Hi, today we are going to be going through two different ideas. The first idea is sequences, and the second idea is an introduction to series. And I do have old videos of these lessons, so should this not make the most sense to you, feel free to check those out as well. We'll start right out. A sequence is just basically an ordered list of numbers, so let's write that down. And so what I mean by an ordered list is in contrast to something like a grocery list. If I had a grocery list, it wouldn't really matter what order we put the items in, right? There could be bread, there could be fruit snacks, there could be bananas. And if we get those things in any order in the store and bring them home, it's going to be the same end result. However, a sequence is not like that. A sequence is where the location of the value actually matters in our list. So here are some examples down below, and you saw this idea in the skills review the other day as well. So these are just sequences, and we're trying to find formulas for the sequences. If you look at the first one, you might say, well, the pattern from one term to the next is adding 1. And you might think that that's what we want to represent. That's what I would call thinking recursively. You're thinking from one term to the next. But the real task here when you want to write an explicit formula is to say, well, this is the first, second, third, and fourth term, and the position of the term matches the value of the term. So a way that I would write that mathematically is this. Now, the t sub n does not need to be a t. It does usually have a subscript, and the reason for that is this would allow me to then substitute in and say, well, t sub 4 is 4. Term 4 is the number 4. And so my two variables are n and t sub n, or it could be some other letter that isn't t, okay? The next one, therefore, if we think again about first, second, third, and fourth terms, the fourth term is 8, the third term is 6, the second term is 4. That means that every term is 2 times the position of that term, right? Think about the fact that these are like having these ordered pairs, right? And so if you were thinking of that like an input-output, like a table, right? The pattern is you take the input times 2. And that's what we're saying in that formula. The next one I do think we had on the skills review. This is just an alternating pattern. And to get signs to alternate, we just need to have a negative raised to a power with the negative in the parentheses. And then since I want this to start positive, I'm going to have a 1 added on to that n, so that my first exponent is a 2, the next exponent is a 3, the next exponent is a 4, and all those even exponents are going to yield positive results. Then the next one, you could say, well, all of the numerators are 1, so in my formula I need to have a 1 always, and then the denominators go 3, 9, 27, 31. Those are powers of 3. And in a similar manner, the last one, you could say, well, all of these have cosine, so cosine has to be part of the formula. All of them have 1 in the numerator, and then my denominators go 1, 2, 3, 4. So that's going to be my formula. Okay, so that's the idea of what sequence formulas should look like in explicit form. And we have this definition here, and I don't want you to overthink it. Basically, it's just saying, hey, you can think of sequences the same way that you think of limits. So if a particular sequence formula, right, if you were taking the limit of that formula and it has a finite limit, remember that limits are finite, a finite number L that it converges to, then we actually call that sequence convergent. And if the limit doesn't exist, right, for some reason, like there's some oscillation, it doesn't settle down to one value, or there's going to infinity or going to negative infinity, then we say that this sequence diverges. Okay, down here we have some problems, and I want you to try to take a minute on this. I'm just going to record some silence for a bit, and I want you to tell me if you think these sequences have limits or if they diverge. Go ahead and try. Actually, you can pause your video. I'm going to start recording again. Okay, so pause on your end. Okay, and I'm going to come back with answers here. Okay, so this one we would say diverges because those values are going to infinity without bound. This one, the limit of this expression, 1 over 3 to the n, is 0 as n goes to infinity. And so we would say it converges to 0 specifically. The next one oscillates, right? That was the one that went, just between 1 and -1. And so it's not settling down to any one particular value as n goes to infinity. So we'd say that one is a limit that does not exist. So the sequence diverges. Okay, the next one is kind of interesting. It has a number and then a negative, and then a positive, then a negative, and a positive, and a negative, and all of them are getting closer and closer and closer to 0. That actually does have a limit of 0, right? It's going like high, like if this is 0, like this is what Mr. Aronson actually refers to as the dying dolphin, right? Jumping and slowly petering out. Okay, its limit is 0. Okay, so limit is 0. So that means that the sequence converges. And then the last one, we're getting the argument of the cosine function is getting smaller and smaller and smaller. So we're approaching cosine of 0, and cosine of 0 is 1. So the limit of this is 1, which means, again, we have something that converges. Okay? So basically, if the limit exists, finite limit exists, then for the sequence as n goes to infinity, then we say that that sequence converges. Otherwise, we say it diverges. And this points out to us that we can really be thinking of limits and functions as being related. So even though when we're talking about sequences, we're talking about discrete sets of data, meaning that I just have points. I just have these specific numbers, number, right? I could think of it like this kind of set of data, right? Where I have 1, 2, 3, 4, 5, 6, 7 as my inputs, the sequence values as my outputs. So I can think of them as these discrete functions that are just made of certain values, but the behavior of the sequence and the behavior of the related function that has all real numbers as its domain are one and the same. So if the limit of the connected function is some finite limit, then the corresponding sequence has that limit as well, and that means that it would be a convergent sequence because it actually has a finite limit. Okay? The little bit down here, I don't really think I actually care to do. Okay, so I think I'm going to have you cross this out. There's a little bit of emphasis in your textbook sometimes about whether things are monotonic or not. Monotonic just means only increasing or only decreasing. So if you see that somewhere, that's what it means. But really, on retrospect, I don't think that's a very important chunk for us to deal with. So let's not, okay? All right, going on to the next page. There are, and the next piece of paper, there are 8 problems that I want you to try. All of these say find the limit of the sequence if it exists. So sometimes you might have something that has behavior that doesn't settle down, right? It's like the 1, -1, 1, -1, or that goes to infinity. In those cases, the limit doesn't exist. The sequence is divergent. If the limit does exist, please tell me what it is. So that's what this question is asking about. You will find answers to it in the next video. Come back to that when you're done with these.